So for chemical bonding so far, I think you've been seeing a couple of interesting points that are coming up in your study. First, recall that we're going to have three different basic types of bonding. So the bonding types are going to be of ionic. Ionic bonds involve a transfer of electrons, so it's a physical movement from one place to another. And if we think about it from the standpoint of the orbital notation, it can actually make things maybe appear a little simpler. So if I took lithium, recall that's going to be 1s2 and 2s1. So that 2s electron there is not necessarily something that the lithium needs. In fact, if it can get rid of it, then it's going to be of the noble gas configuration for helium. So that would be a desirable state, and remember this explains why lithium is going to have a low first ionization energy, a low electronegativity, a relatively large atomic radius, and so forth. Well, if we put it in close proximity with another element, say fluorine, for example, fluorine would be 1s2, 2s2, and then it's got the 3p orbitals, right? So 2p, and then we fill 1, 2, 3, 4, 5. And you can see then that there's a space here, right? So we've got an opportunity for an electron to be placed there. Well, fluorine, if it was to gain an electron, would be a lot like its noble gas counterpart, which would be neon. So that's a desirable state for fluorine. So in fact, in a chemical bond involving ionic, what we're going to see is that electron from the 1s in an example with lithium will go to populate that last orbital and fill it completely to make a fluoride ion. The fluoride ion then being negatively charged, the lithium atom losing its electron becomes positively charged, and we then therefore are going to have a force of attraction. A chemical bond in and of itself is a force of attraction between two or more atoms. And so then the composition of the molecule that would be formed here would be lithium fluoride. So there's sort of an orbital approach to it. If you had something a little bit more complicated, perhaps something like lithium and nitrogen, right? So I'm going to draw nitrogen first, 1s2, 2s2, and 2p, 3, so half fill. Okay, well, lithium is not going to be able to accomplish that in and of itself, but our 1s2, 2s1, if we were to do this a few times, so one lithium ion, one nitrogen with an extra electron. If we then had a second lithium atom following the same idea, its one valence electron transfers to complete the second orbital, and a third lithium ion, or atom, transferring its electron to the nitrogen, then achieving each of these with a helium notation and then nitrogen with a neon notation, we would have 3 Li pluses and 1 nitrogen with 3 negative charges. You see a balance of charge exists. We have 3 positives and 3 negatives, and in fact that combines if we were to write the chemical formula, Li3N. So that's not unfamiliar. We've written chemical formulas before. That is exactly what we're going to be expecting to see, at least in terms of our modeling. Well, the second type would be the covalent bond. And you might remember then covalent being the sharing of electrons. It's the overlap of the outer shell and the minimization of the energy. Again, forming molecules results in a minimization of the energy between two atoms. So simplest example here would be, say, hydrogen with its 1s, 1 electron. And let's say that we had another hydrogen nearby, hydrogen number 2 with 1s, and let's say electron would be written like that. Well, each of these would like to have an extra electron, right? Because then they become like helium. In a covalent model, then we model that as a sharing opportunity, where then the two outermost portions of the electron orbitals, the 1s's, will overlap to form a bonding pair between the two. And so that then becomes a literal sharing between the two atoms. So as an example too, if we had oxygen, we have 1s2, 2s2, and then our 2p orbitals, x, y, and z. So we'd have 1, 2, 3, 4, and we can see that there's vacancy for 2. If we combine lithium, there would be a physical transfer. Then there would be a charge change. The oxygen would gain negative charge. The lithium would then be positively charged, and we'd have a balance of charge based on opposites attracting. In the covalent model, we'll see this a little differently. The 2p from the second oxygen atom then, 1s2, 2s2, 2p. Let's see now, we'll draw it like this. Right, so then the overlap between the two orbitals, the two 2p orbitals there, that are not filled. They're half filled in this case, but when they form the bond, it fills between them. And so then we form a chemical bond between oxygen, molecular oxygen, having 2 pairs of electrons between it. And we'll talk more about the lone pairs and so forth at another point, but at this point, at least you can see the basics, right? We're talking about ionic, we're talking about covalent, and of course there's that elusive metallic bond, which is where we see the sharing of electrons between many nuclei. So they're free floating. The electrons then will go between the nuclei of metallic atoms, and they're free floating. So they can kind of go along like so, they can change path. Okay. What we see then is that because we have mobile electrons, it explains things like electrical conductivity, it explains things like heat conductivity. It explains a lot of their character that we would ordinarily not see in an ionic or a covalent structure. So we won't address the electron motions within metallic. It's far too advanced for where we need to be in the course. Well, the last thing that I want to look at here before I turn you loose for the balance of the period is to consider what happens when we have atoms and to distinguish what